Hello, my name is Ben Hartguy, and I'm here with Ben Chavez. We are looking at a particular problem for our Systems 2 presentation. First off, I wanted to explain this picture. This picture is basically just a branchless tree, and this is something that's going to appear in our problem later on. Let's go ahead and check out the problem first. This is our problem. Mainly what the question is asking is, with this particular C++ code, if it's compiled with GCC, this particular code takes a pretty large vector with many entries, calculates basically some running sums during throughout going through that vector. And what's happening here is that when this code is compiled with O2, it actually runs faster than when it's compiled with O3. And we want to explore why it is that that's happening. And again, just as a reminder, O2 is a collection of optimization flags. O3 is also a collection of optimization flags. We'll get into the differences here shortly. Let's go ahead and go back to the slides. Yeah, and here's some of the things that we did to do these comparisons. We obviously compiled with the two different optimizations. We looked at the flags that each of those optimizations use. We also compiled using different compilers. We'll see why here in a second. That we actually had to download an older version of the compiler to even see what the problem was in the first place. And then we also look at assembly instructions to see some differences. And we use a makefile to create basically some organization as to what we're going to produce as far as what output is and what comparisons we need at the time during the presentation.
Like Ben said, the goal here is to get us to a solution, but the way that we want to do that is specifically to take you through our debugging process. So the way that we approached this problem began with us compiling with GCC 9.3, which is our recent version of GCC. And so basically I've got the compilation going right here, or sorry, not the compilation, the performance of the algorithm or the program. And what we can see here is that we have this optimization 2 flag, which is supposed to be less optimized than the optimization 3 flag. However, if we see optimization 3, we'll see that the time on this is actually faster than it was with the optimization 2 flag, which is what generally you would expect. However, in this case, we were hoping to get some sort of error here, and that's not what happened. So essentially, the next thing we did here is we ran a few different versions of GCC to figure out if we could recreate the problem on any other versions. Ultimately, we basically had trouble until we got down to 4.9, which is what is used in the problem. Once we were able to get that going, we ran it again, and as you can see here, optimization 2 is actually outperforming optimization 3. So first step in debugging, recreate the problem. Now that we've done it, kind of the next thing to do is figure out, what is actually causing this discrepancy, and Ben's going to take over and discuss that some more.
So what we're going to look at now is the comparison of the flags added on to O2 that make O3. And so the very first thing we can do is actually see what those flags are. We'll go ahead and run a command that produces those flags. And so if you look at those two lines there, we have the help optimizers produces, compiled with O2, produces the flags that are enabled and disabled, all the flags, but some that are enabled for O2 and disabled for O2. Also, you can look at the same thing for 3. This is the kind of idea as to what kind of file you would be looking at here. I don't have both of them for right now, but we're just sort of looking and seeing that some of those flags are enabled, some are disabled. This is in particular is for optimization 2. And what we want to do is find the differences. And so what we're going to look at next is we're going to look at the runtimes, starting with basically the O2 optimization, O3 optimization, and then we're going to go from O2, adding on specific flags that are added on to O3 and see what our runtimes look like. So here we have optimization with O2 and O3, which is the main problem, right? The runtime is much slower. And then we have individual flags added on to O2. And you can see here that the flags that are added on to O2 that add up to O3, they all have approximately the same runtimes until you get to ftree vectorized, which has a much slower runtime. So we suspect that this is where our issue lies.
So now that we know which flag is essentially causing the timing discrepancy, essentially going forward, what we decided to do was, rather than continuing to run compilations on both the O2 flag and the O3 flag, basically going forward, we are just running it on the O2 optimization and then O2 with ftree vectorization. In terms of debugging, we know what's kind of causing it, but the next thing that we wanted to think about was like, is there any way that we can essentially break this output or break this performance discrepancy with our input code? And so here is the file again, and like we saw with this code, it's doing a nested for loop, and here we're just kind of doing an iteration through our kind of data array. And so basically we wanted to test this and see what different manipulations could we do to our data array or to the way that it's iterating over it that could impact the performance. And so I went ahead and ran these prior to the presentation here. And so these are the different variations that we did. So optimization O2 with the F-tree vectorization. And so basically this is the additional flag. And note that both of these have the array sorted. And so this one you can think of as being synonymous with the O3 flag. And so this one is running slower than O2, and that is expected. Here, I passed in the array so that way it would be unsorted. And we're seeing some timing discrepancies here we'll want to come back to. Here we passed in an array that is sorted in reverse. And then here, basically, rather than traversing our array from 0 to the end of the array, we decided to traverse it basically starting at the end and going all the way down to 0. And as we can see here, basically the performance times throughout all of these are pretty much in line with what we were expecting in terms of the O2 flag outperforming the O2 vectorization, with the exception of this unsorted here. And so basically what the key takeaway here is like, okay, so if we pass in an unsorted array to our program, any optimization that was causing a slowdown in the O3 is actually gained. So O2 is performing way slower than O3 or with a vectorized free. So essentially we were able to break our program and to kind of get the results to flip.
So we know that the added flag F-tree vectorize causes the issue in runtime. What we want to do is explore F-tree vectorize a little bit more. And so what we can do is run this command fopt info-vec missed, which will allow us to see any missed opportunities for vectorization in your code. So let's go ahead and run that. And you can see here that there are many missed opportunities for vectorization, which may indicate some issues with the runtime.
So next up, we wanted to talk about branchy versus branchless code. Now, this is instruction pipelining, which is a way to implement instruction level parallelism on a single processor. And so by that, what I mean is that there are 4 parts to any process here. And the first one is going to be fetch. The next one's going to be decode. The next one is going to be execute. And then the fourth is going to be write back. And so basically we could think of this little chunk here as a single, for our purposes, a single loop in our for loop. So in this top example here, we could see that this pattern repeats 3 times. And so essentially that would be the equivalent of 3 passes through our for loop. Now, if we're going to focus on this picture down here to the left, essentially we could see that keeping with our example of the for loop, we could see that this is one iteration through. Now, if we think about this being on a scope of time, then we can see that during our decode phase of this first iteration, we've already started on the next iteration. And as we finish up the write back of the first iteration, we're already on to more than halfway through a couple of the other iterations and working on the fourth. This is important because essentially the way that this works is it's based on your code making predictions on the conditional statements. This is, like I said, this is the branchy version. This is a branchless version. And so you can see that this is all happening in order without any kind of simultaneous computations happening. Now, this seems like it would be the optimal choice, with the exception of when your code is not predictable. So when your program is trying to make predictions and those predictions are coming out to be incorrect, then essentially, as we can see here, if your predictions are incorrect, your computer had already computed some of this, if this was iterations through. And so it would have to recompute all of that. And so it would be kind of doubling up on some of the work that it had already done. And so that's kind of the main difference here between branchy and branchless code. Branchy is going to be, multiple processes happening in step with each other, whereas branchless is going to be kind of everything all at once. A couple of quick examples of this is going to be this first if statement. We could see general conditional here. And then here with our branchless version, so the top's going to be branchy, the bottom's branchless, we could see that we were able to rewrite this statement in a way that gives us the same output, but without any actual conditions. So A greater than B is going to result in either 0 or 1. Similarly, A less than or equal to B is going to result in 0 or 1. And then, multiply that out by A or B, and we get the same that we would have up here, except for this would have been quote unquote branchy, and this is branchless. A similar kind of example down here. Next up, we want to look at the actual assembly code and kind of apply this knowledge to the assembly code. This is basically just kind of showing us the key differences between the two different compilations. On the left, we have the simple O2 optimization flag. On the right, we have O2 flag with F-tree vectorization. And then down here, we basically have the different pieces of the assembly code and their relation to the program. So if we look a little bit closer at the assembly code, we'll see that on the top here, we've got the O2 optimization, on the bottom O2 with F-tree vectorized flag. And we'll see that the key difference here, again, is this cmove instruction. Essentially what this is doing is this is the points that we assign the sum or the new data point to our sum if some conditions met. So we're kind of looping through, we're calculating sum every single time. This is the branchless version. And then we're adding, if the conditions met, we're adding this new sum to this right here. In contrast, this is our O2 optimization flag. This is our branchy version. Basically, it's saying, hey, if this condition is met, then calculate sum and add it. Otherwise, keep going, and just kind of keeps going through, and it's only calculating sum if and when the conditions met. The key takeaway here is that here we're computing sum every single time, and up top we are not. So up top, that is likely going to be the optimal version if and when our conditions are predictable. So now to tie this back slightly to what we had looked at earlier with passing in different types of data or working with the data differently. Now, if we recall, when we passed in an unsorted array, it actually misaligned this kind of performance outcome. So O2 is actually performing much slower than the O2 with vectorization. And so essentially what we can attribute that to is the predictability. So when something is unsorted, it's not predictable, versus the other different ways that we passed in the data were more predictable. And so therefore this this branchy version was not having to recompute anything. However, when we passed in something unpredictable, we were having to recompute a number of these calculations because our conditional predictions were wrong. And that's why the O3 or synonymously the F-tree vectorization flag was actually quicker, because it wasn't making those predictions.
Right. So basically what we want to do is just kind of summarize what we did today. Some of the things we did, we looked at the assembly to see the differences with the different flags, different optimizations. Assembly basically is always a good way to see if your code is running well with one version versus another. Another thing that we looked at, the optimizations may not always work as intended. I mean, here we had an optimization that was added onto O2, which you would think would make it run faster, actually made it run slower than just generic O2. So we may want to dig into what optimizations those are and see what the differences are. It may turn out that it may not optimize based off of the way the code is written. We can also look at potentially writing code to produce a better chance of optimization, to improve the chance of optimization, which we can take a look at that here. So you see here we have the optimization O2, and then with the added vector F-tree vector flag, and then also two other versions of the file with much better runtimes than the vectorization flag alone. So basically, we have two other files that adds the vectorization flag, but the files are written differently so that it turns out that the runtime turns out to run better than just the original file with just the vectorization flag. Yeah, we can see here that in this version, sum is declared as a global variable, and you can see at the bottom here, when we run that, the runtime has better performance than just, but again, this is declaring it as a global variable, but adding on the vectorization flag, and it does improve the runtime without declaring it as a global variable. And then on the second one is a similar idea in the sense that you get a better runtime, but again, the inner loop is written a little bit differently. It's without the if-then statement, and so we have an inline if-then, and it turns out that runtime is also much better. In fact, it's the best of the four. And so you can see that writing code definitely makes a difference in optimization. Let's head back to the slides here. So we can write better. Definitely writing code obviously makes a difference, and we can really improve. We can really work with the optimization flags to potentially produce better running times. And then also, the last thing is just to quickly say that, this was based off of a GCC compiler that was older. It does seem like the F-tree vectorization flag does perform better with that particular code later on. So that's another thing to explore at another time. So that concludes our presentation. I'm Ben, and Ben is here. We've both been working pretty hard on this, and thank you guys for listening.